What's up guys, Patrick here, welcome back. Moving on to the next topic, still dealing with L'Hopital's rule, we're now going to talk about indeterminate products. So this is a different type of indeterminate form. If you remember at the very beginning of the section, I mentioned that we're going to go over a bunch of indeterminate forms. And the two that we've covered so far, to do a quick review, is if we have a limit where if we did a direct substitution, it's going to be in one of these two formats here. And to be a little bit more specific, these two formats, they are called indeterminate quotients. Okay, so to kind of show you from a high level of what's happening, I've been using this term indeterminate formats or forms, but these are going to fall into different categories. So we're going to have indeterminate quotients, which we already covered and did a bunch of examples on. Now we're going to be covering indeterminate products in this video and actually over the next couple of videos. And then later on in the section, we're going to cover indeterminate differences and then indeterminate powers as well. Okay, so just in case you're getting a little confused with the terminology, this is kind of from a higher level of what's happening. Indeterminate forms is just a general expression, but indeterminate forms are going to fall into different categories, and we've covered this already, right? These are the indeterminate quotients. We're now going to cover this, and then those two indeterminate forms we're going to cover later on in this section. All right, so these are the two formats that we've covered so far here. And we said that if a limit is in one of these formats, then we can potentially apply L'Hopital's rule. Not always, it's not always going to be efficient to do so. I showed an example of that as well. But we can potentially apply it and then get an actual value for the limit instead of it being in this indeterminate form over here. Now, another thing I mentioned is that it has to be one of these two formats. You can't mix these. So for example, you can't have 0 over plus or minus infinity, right? Because you're going to have a very small number over a very large number, which just gives you a very small number. And you can't have plus or minus infinity over 0, right? A very large number divided by a very small number is going to give you a very large number. And that's a common mistake. Sometimes they'll give you limits and it will be in one of these formats already, right? So we'll approach 0 or approach plus or minus infinity, but then students will apply L'Hopital's rule on this. But this is not an indeterminate form. It has to be one of these here. You can't mix and match the 0 and plus or minus infinity when you're dealing with quotients. However, when you're dealing with products, when you're multiplying two functions, then you do mix them. So indeterminate products are going to be in this format, plus or minus infinity times 0, or 0 times plus or minus infinity. So these two forms here are called indeterminate products. And again, it has to be one of these. So you can't have 0 times 0, because a very small number times a very small number is just going to approach a very small number. And then you can't have plus or minus infinity times plus or minus infinity, because that's just going to give you plus or minus infinity. So these products here are not indeterminate forms. It has to be one of these. And the reason why is because if you have a function going towards plus or minus infinity and then another function going towards 0, you don't know which one is moving quicker, quote unquote. So you don't know if this one is going to get to positive, negative infinity faster than this one's going to get to 0, or you don't know if this one's going to get to 0 quicker than this one's going to get to plus or minus infinity, or you don't know if they're going to compromise at a certain number, right? So we have to apply a different kind of strategy if we get limits in these formats, and I'm going to show you, I'm going to go over an example in this video, and then over the next couple of videos of how we deal with this. Now, how we actually deal with this, indeterminate products specifically, is we actually take these and we convert it to an indeterminate quotient. So here's what I mean by that. What you can do, actually just as a review, if you remember, if you have an expression, that's the same thing as 1 divided by the reciprocal of that expression. I just want to go over that fundamental right there. That's what we're going to be using to deal with these indeterminate products, right? So if you have an expression or a function or a variable, that's the exact same thing as 1 divided by the reciprocal of that expression. Both of these are the exact same thing. And we're actually going to be using this format. So what we would do is, if we're given this here, we're either going to take this plus or minus infinity and put it in the denominator. So what we would do is we'd keep the 0 up top. And then this here, we would convert to 1 over plus or minus infinity, like that, applying that fundamental that I just went over. So we're either going to take this function and put it in the denominator, but then we have to make it a reciprocal to make these equal. Or we're going to take this function and put it in the denominator. So we would then have plus or minus infinity over the reciprocal of that function right there. And now notice that what's going to happen with this? Well, we're going to have 0 at the top, a very small number. What's 1 divided by plus or minus infinity? Well, that's going to go towards 0 as well. Right? So we took this and converted it to this format. And then what we could do is we could potentially apply L'Hopital's rule on this over here, like we did in the previous videos. And then notice this here, we're going to have plus or minus infinity. And then 1 divided by a very small number is going to be plus or minus infinity, which is going to be this format. So then we could potentially apply L'Hopital's rule on that. So I'm going to go over specific examples, but just want to give you kind of a general overview that when you're dealing with indeterminate products, this is usually the general process you're going to do. You're going to take one of these functions and bring it down to the denominator and make it a reciprocal. And you got to specifically look at the functions and see which one is easier to deal with as a reciprocal. I'm going to talk about that too in specific examples. But when you convert it to this, it's going to be in this indeterminate form. It's going to be an indeterminate quotient, and then you could potentially apply L'Hopital's rule. So let's show how this works through an example. So let's say we got the limit as x approaches positive infinity of x squared times sine of 3 over x squared. So notice that we got two functions that are multiplying by each other. We got this x squared times sine of 3 over x squared. So what's going to happen if we do a direct substitution? If we plug in positive infinity for x squared, notice that that is going to go towards positive infinity. And then if we plug in positive infinity for this x here, we'll have 3 over a very large number, which is going to be a very small number. And then sine of a very small number, a number very close to 0, that's going to go towards 0. So this function's approaching positive infinity. This function here is approaching 0. So notice that that's an indeterminate product. So we can't do a direct substitution. We don't know what's going to be happening here. So what we got to do is we got to convert this to an indeterminate quotient, like I mentioned before. The question is which function are we going to take out of the two and put as a reciprocal in the denominator? So we can either keep the x squared up top and then bring the sine of 3 over x squared at the bottom, and we'd have this reciprocal here. Or we could keep the sine of 3 over x squared at the top and bring the x squared to the bottom and make it a reciprocal. So is this function going to be easier to deal with or this one? My opinion, this one is going to be easier to deal with, right? Versus this one, you can maybe rewrite this as cosecant of 3 over x squared, but even still then, that's going to be a little bit more complex than this. So I'm going to use this format. So what I'm going to do is I'm going to take this limit now, and I'm going to rewrite it as the limit as x approaches infinity of sine of 3 over x squared all over 1 over x squared over this function here. And now notice if we do a direct substitution, what's going to happen is we know this is going towards 0, as we mentioned, but now this 1 divided by a very large number is going to go towards 0 as well. So this and this are the exact same thing, but now notice that this whole function has this indeterminate form, an indeterminate quotient. So we change it from an indeterminate product to an indeterminate quotient, and now that it's in this format, we can potentially try L'Hopital's rule on this. And so if we apply L'Hopital's rule, what we would do is take the derivative of the numerator. So the derivative of sine of 3 over x squared would be cos of 3 over x squared. But then we got to take the derivative of that inner function. We got to apply the chain rule. So I took the derivative of the outside. Now, to take the derivative of 3 over x squared, I'll do it on the side here. I'm going to take that x squared, bring it up, and change it to a -2. So just apply the power rule on this. Bring the -2 down, so we'd have -6, x to the -3. So we'd have -6 over x to the 3, like that. So this here is the derivative of 3 over x squared. So I'm going to multiply it by -6 over x to the 3. And then we got to take the derivative of 1 over x squared, which is just x to the -2, which is going to be -2 x to the -3, which is -2 over x to the 3. So now that there is the derivative of that. So we took the derivative of here, took the derivative of the denominator, right? Applied L'Hopital's rule. And then from here, what you want to do is you actually want to try to simplify this. So notice that we're taking all of this and dividing it by this fraction, which is the same as multiplying it by the reciprocal of that fraction, right? So dividing by this fraction is the same as multiplying by the reciprocal of that fraction. And now notice what's going to happen. Those cancel out. -6 divided by -2 is +3. And then what we could actually do is take that +3 and factor it out. So we'd have 3 times the limit as x approaches infinity of cos of 3 over x squared. You don't have to factor out that 3, I just did so. You could take out a constant, I always look to do that. And then over here, notice that if we do a direct substitution on this, 3 over a very large number we know is 0. So we'll have cos of a very small number, or cos as this bracket approaches 0. So we could actually take this and rewrite it. If we're going to be really proper, we could bring in another variable like that. You don't necessarily have to do this. I'm just being a little picky with the format. But basically, as x approaches infinity, this bracket approaches 0. So we can rewrite it as, and it actually approaches 0 from the positive side if we're going to be even more specific. Right? This 3 over x squared, it looks like this. So we're approaching 0 from the positive side. Right? It doesn't matter too much in this question, but it can matter in other questions. So we're approaching 0 from above, right? So this and this are the exact same thing. And then as cos, as that variable approaches 0, cos of 0 is just 1. And so we would end up having 3 times 1, which final answer is 3. Right, so depending on your teacher, depending on your prof, you may not have to do this step here. You could just tell that this is going to go towards 0, and then you're going to have cos of 0, which is just 1, and then 1 times 3 is just 3. But if this is a short answer and you got to show a more proper format, that's how you would show it. So either way, this limit is approaching 3. Right? So a quick review, we took this indeterminate product, changed it to an indeterminate quotient, applied L'Hopital's rule, and then it was just algebra to get that final answer of 3.